The next step, to convert inches into centimeters. We're on the right track here. We want meters, and we have so far gotten to centimeters. I gave you this conversion. 1 inch is equal to 2.54 centimeters. Now you guys tell me what's next. Centimeters to centimeters to meters. And this is where I would ask you to use that acronym you wrote up on your papers. I want you to look at that acronym and tell me which one is larger, meters or centimeters. Meters is larger. So after you've identified which unit is larger, I want you to go ahead and put a 1 in front of the larger unit. That means that the other unit is going to be 10 to a positive power. If you always put 1 in front of the larger unit, it will always be 10 to a positive power. You don't ever have to worry about negative exponents. So how many spaces is there between meters and centimeters? So meters is the base unit because there's 3 units. Centimeters is here, so you go 1, 2. That means it's going to be 10 to the second power. Oh, shit. It doesn't matter if it's in the numerator or in the denominator. If you put 1 in front of the larger unit, the exponent here will always be positive. And now we can cancel centimeters. If we answer this right now, we have our answer in meters per day. So we're still not quite there yet. So this one is done. We're not going to cancel this unit anymore. Now if we want to cancel day and convert it into another unit, where would it go? Yes, to hours, but in the top or in the bottom? Am I writing day? We have to write day in the top this time because it has to cancel out with the date that's down here. And days into hours. Wow, this is so long. In one day, we have 24 hours. Now, how do we go from hours to, I'm going to go directly from hours to seconds because I'm running out of room. We can do that just as long as you know the conversion. How many seconds are in 1 hour? 3,600. You could have also done 1 hour, 60 minutes, 1 minute, and 60 seconds, but this just combines it into one step. So hours now cancel. And notice that the units we're left with, after we've canceled all of them, is meters per second. So from this point, what you should be doing, because these are fractions, multiply everything in the numerator and divide by everything in the denominator. And if you do that, you should be getting Is everyone getting 0.254? No? Oh wait, divided by 24. Is everyone getting 0.0105? 0.0105 meters per second is how fast this hamster is running. In meters per second. Any questions? Is the sign-in sheet still moving? Where is it now? Okay, great.
Excuse me. Sorry.
Can I change the page? Oh. Don't worry too much about significant figures or rounding that very last number. Your exams are multiple choice. It'll be obvious which one the answer is. For this next question, sometimes they're going to give you units that you may have never heard of. When they do that, they have to also give you the conversion factors for those units. So I also don't really know what most of these units are. However, I can still convert between them if they give me what each one is equal to. So we're going to start off this question the same exact way. We have the spiral galaxy that is 3.0 times 10 to the 6 parsecs away from Earth. 1 PC is a unit used in astronomy and is equivalent to this many astronomical units. And then 1 AU is equal to this many kilometers. What's the difference between Earth and the spiral galaxy M83 in meters? We're going to start off the same way. Write the number that you're given. 3.0 times 10 to the 6th PC. The direction for this problem should be clear because we need to cancel PC. And the only unit we know between parsecs and the next one is AU because that one was given. 1 PC is equal to 206.265 astronomical units. I still don't know what any of these things are, but I can convert between them. You can multiply. How are we canceling astronomical units? What goes in the denominator? And what's going in the numerator? And what number goes in front of kilometers? And what number goes in front of AUs? Right. Now, if we have to convert from kilometers to meters, how would we do that? Where are we putting our units first? Kilometers in the bottom, meters in the top. Which one is larger? Kilometers is larger, so I'm going to put a 1 in front of kilometers. How many spaces are there between meters and kilometers? 3 spaces, so it's going to be 10 to the 3rd in the top. Positive exponents. Now if you solve this, you just get your answer in meters. You guys should be getting a really, really large number. 9.03 times 10 to the 22nd meters. How many liters are there in that number of micrograms of a given substance? And then I gave you the density of the substance is 3.21 grams per ml. Starting off the same way. Write down the given number. Micrograms. Where do you guys think we're going to go from micrograms? So we're going to go from micrograms to grams. Which one is larger? So grams, you got a 1 in the front. How many spaces are there between grams and micrograms? Make sure you're counting those 2 empty spaces. 6 spaces, so it's going to be 1 gram is equal to 10 to the 6th micrograms. What can we do from here? If we have to get to volume and we're at grams. So most of you know the equation for density as density equals mass over volume. And if we solve this, we have an answer in grams, so we have a mass. And then I gave you the density, so you could technically solve for volume. One other way you can use density is as a conversion factor. So we can use it just the same way we've been doing the rest of these conversions. You can go from grams to ml by putting 3.21 grams for every 1 ml because that is the density. Density is also a conversion factor, or you could use this equation. I prefer to do it this way so that I don't have to get multiple answers along the way and then I can just get my answer at the end. You all see how I use density as a conversion factor. The density is given as 3.21 grams per ml. So in 1 ml, we have 3.21 grams. Grams will cancel out. Yes. This one? So 3 times 10 to the 6 times this number times this number times 1,000. Did anybody get this number? Okay. So let's all put it into our calculators and make sure we're all getting the same number. because that's, believe it or not, an important part of your exam. It's times 10 to the 8th, if I didn't write that number clearly, times 1,000. Oh wait, I'm getting a similar number, but it's 9.2, 5, 7, 10, 26. Thank you for pointing that out. I do make mistakes.
I'll take my chances with you too.
Good catch. Oh, this one? So you also did it wrong, but that is different. Are we all okay with this one?
The first one is drop, right? Isn't there one?
So we use density as a conversion factor here. We've now gone from grams to ml. I would have solved it at this point and have an answer in ml. That's not quite what the question is asking for. We can then go from ml to liters. Which one is larger? And how many spaces are there between liters and milliliters?
What if that did? Because when I was looking at fucking professor, he like did a bigger one. We're all here to do stuff. I said that you one time. What? Yes. Really? Do you want me to help you study? It was such ridiculous. I remember that one.
Which one? 10 to the third, the last step? Yes. So actually, I'll explain this step when we went from grams to micrograms. So if you look at the acronym here, it doesn't matter if you start here or if you start here, you just are counting the number of spaces. So if I'm at grams, and then I want to get to micrograms, all I have to do is go 1, 2, 3, 4, 5, 6. Remember, these count as 2 empty spaces. So there's 6 spaces between them, and that's your exponent here. So it's going to be 10 to the power of 6. So in this question, the answer was 0.0180 liters. Okay, and this next one, I would skip it because we've done a lot of them, but this one, I really want to point something out. So we're going to do it anyway. Oceanographers often express the density of seawater in units of kilograms per cubic meter, so kilograms per meters cubed. If the density of seawater is 1.025 grams per centimeters cubed, what is the density in kilograms per meter cubed, per cubic meter? So for this one, it's a little bit different. We're going to start by writing our given number, grams per centimeters cubed. And this is a side note, you don't need it for this problem, but what is centimeters cubed the same thing as? Milliliters. 1 centimeter cubed is equal to 1 ml. We'll start by converting grams to kilograms. Grams has to go on the bottom, kilograms will go in the top. Which one is larger? Kilograms is larger. And how many spaces are there between kilograms and grams? So 10 to the third. The next one is going from cubic centimeters, so centimeters cubed, to meters cubed. In 1 meter, I'm going to write it down here so that there's space to do the rest of the problem. In 1 meter, how many centimeters are there? 1 meter is larger, so I can put the 1 there. 10 to what happens? Second centimeter. There's 2 spaces between meters and centimeters. In 1 meter cubed, however, we have 10 to the second centimeters, but everything gets cubed. So when you cube something, it's both the number and the unit. So this is 1 cubed meters cubed is equal to 10 to the second cubed centimeters cubed. still just 1 meter cubed is equal to, how do you solve that? So you have to multiply 2 times 3, and it's going to be 10 to the 6th centimeters cubed. If you did 1 meter cubed is equal to 100 centimeters cubed, that would be incorrect. When you cube units, you also cube the number that goes with those units. So in 1 meter cubed, we have 10 to the 6th centimeters cubed. I would just take a picture of this. If it doesn't register right now, you might be able to look back on it later and then just follow the math that I did. But then centimeters cubed cancels, and when we solve this problem, it's just going to be 1025. Right, just multiply by 1,000. I'm sorry, I know space is tight, but there is room kind of like up here. If somebody wants to come and like stand here, they're welcome to. There's a screen right here that has all the stuff that I'm going over. I already gave away the chair though. Any questions?
She said you can stand right in front of her screen.
Who has the sign-in sheet? Anyone?
That was literally somebody sitting right in front of
Thank you.
her.
Yes. This one? Okay, so I'm noticing this is a little, because this room has never been more than like half full for the first exam review, but there's a lot more people here than I expected. I usually don't send the answers, but I will snap a picture of all of these pages and then post them on campus, because I know this is getting a little bit difficult to pay attention and write down. So I'm gonna snap pictures of everything that I write down on campus. That kind of concludes it for chapter 1. Those were the main concepts and then the main ideas we converted units. Chapter 2 starts talking about what atoms look like. So an atom, you have a nucleus in the center. Nucleus is made up of protons and neutrons, so the dark ones we'll call it protons, that's a neutron. And then the electrons surround the nucleus in what is called the electron cloud. What is in the nucleus of an atom? So the nucleus is made up of protons and neutrons. And then whatever is not the nucleus is where you have your electrons. Protons is the same as protons is equal to that atomic number. So on the periodic table, it starts off with 1, 2, and then it just keeps going up by 1. That's the number of protons in every one of the atoms. Neutrons, actually protons plus neutrons, is the mass number. And then if something is neutral, the number of protons is equal to the number of electrons. So to answer these questions, really quickly, what is the mass number of an iron atom with 30 neutrons? You saw this number on the exam. First, you have to come up with a chemical symbol for iron. Iron is Fe. The next thing you're going to do is go to the periodic table and look at the atomic number of Fe. Or, sorry, not the atomic number. Yeah, the atomic number. So the number of protons. Fe has 26 protons, and I told you 30 neutrons. Therefore, the mass number, yes, 26 plus 30, protons plus neutrons gives you mass number. How many protons, neutrons, and electrons are in, that's a 64 Zn atom. Zn is zinc, and this number in the top left corner is always the mass number. Sometimes there's a number written down here. What is that? The atomic number. Do you have to write it there? No, because you can go to the periodic table, and it's right there. The atomic number, the number of protons for an atom does not change. So if we have a mass of 64, how are you gonna find the protons, neutrons, and electrons? We'll start with the easy one. What's the protons? 30. How do you get the neutrons if you know the mass number and the protons? So how many neutrons do we have? And then how do we know how many electrons we have? Is it always going to be the same amount of protons? Not always. In this case it is. Why?
It's not an ion.
So a few of you are saying it. There's no charge up here, so that means this has to be a neutral atom. All of the positive and negative charges cancel out perfectly, so it's the same as the number of protons. The mass of an atom of manganese is this many AMU. How many neutrons are contained in one atom of this element? So this is the mass number, and we're talking about manganese. So do I go to Mg on the periodic table? Manganese is Mn. How many protons are in manganese? 25. And then how many neutrons do we have? 30 neutrons. Notice how this is 54.9. We're going to round that up to a whole number because we can't have 0.9 of a neutron. So it's just going to be 30 neutrons. 55 minus 25. All right, this next part. This question is actually very important, and in case this is a little bit too small, can you guys see these numbers here? Okay. The next concept are isotopes. What is an isotope? Atoms with different numbers of neutrons. What is an atom with a different number of electrons? An ion. So isotopes have different numbers of neutrons. Therefore, they also have different mass numbers. Correct. So using this notation, I want you guys to point out the pair of isotopes for the element. Tell me which two of these are isotopes of each other. I heard it, so somebody said this one and this one. So we're going to go through why that is. We've already said the number in the top left is your mass number. That is the number of protons plus neutrons. So if we're talking about isotopes, we automatically know those two should not be the same number. They need to have different mass numbers if they are isotopes of the same element. And then if you look down here, what did we say this number on the bottom was? The number of protons. Are those going to be the same or are they going to be different? If we're talking about the same element, they should be the same number. So the key here was to look for the same number of protons, but different numbers for the mass. Notice how 9 up here and 20 down here. This is an element with 20 protons and an entire mass of 9, so that's not even possible. Here, this is the next element in the periodic table. So this has 10 protons. We're talking about a different element entirely. And then this one only has 8 protons. So again, different element entirely. The only two that are actually the same element are the ones with the same number of protons. Are we okay with that? Now, how do we find the average atomic weight on the periodic table? So isotopes, there are many. Each atom has maybe 2, 3 different naturally occurring abundances on Earth. I think I use carbon as an example. I do. Okay. So isotopes, they all occur in different ratios, and then we take that weighted average, and that's the average atomic weight on the periodic table. You don't actually have to know how to calculate percent abundance. I just put this equation in case you're curious. Remember though, percent abundance refers to how prevalent an isotope of a given element is in nature. So not all of the isotopes are found in the same amounts. All the isotopes have, yes, all the percentages must equal to 100. Just remember that fact because sometimes they'll give you 2 out of 3 of the percentages and ask you to calculate. Make sure you're subtracting from 100 to get that third one. And then here is the example. This is a common one. Carbon occurs in 3 naturally occurring isotopes, 12, 13, and 14. So if we took the average of these masses, 12, 13, and 14, what would we get?
100.
We'd get 13. Now, if you look at the periodic table, what is the atomic weight of carbon? It's 12. Why is it not 13? Carbon 12 is the most abundant. Therefore, carbon 12 is going to contribute the most to the average atomic weight. It's like when you take a class and you have like quizzes worth like 1%, homework worth 1%, extra credit is like 1% of your grade, and then exams are like 99%. So if you get an A on everything in that class except the exams, are you getting an A in that class? No. Exams are weighted the most. These isotopes work in the same way. So even though we have one that's 12, 13, and 14 for the mass, carbon 12 weighs the most. So it's going to contribute the most to the average atomic weight. The way we calculate weighted averages, here, you always multiply the percent over 100, we have to convert them to decimals, times the mass of that isotope, plus the next isotope, plus the isotope after that. So we're basically just finding the average atomic weight by taking the proportion that each one contributes and adding them together. Another way they could ask this question that doesn't involve calculating anything would be to give you something like this, but maybe they won't give you the percentages. And they'll ask you, which one do you think is the most abundant based on the average atomic weight that's given? And if it's closest to 14, then 14 would be the most. If it's right in the middle, 13 would be the most. If it's closer to 12, then 12 is the most. So we can tell how abundant something is without really doing any math if we already know the average. Another way they can, and also if the average is like between, or say like the average is some number higher than this, so say it's like 16, these are not even like possible because we also need higher numbers. So they're also going to be like outside the range that they might give you. Be careful with them as well. Please don't pick anything that doesn't even contribute to an average. It's got to be within the isotopes. Did you have a question? I thought I saw a hand up. But we are going to do a couple of problems. If bromine has 2 naturally occurring isotopes, one with this mass and an abundance of 50.69%, what is the mass of the second isotope given that we know the average atomic weight of bromine? So in this question, it's a little bit different. On the exam, if they give you real elements to work with, then they're not going to ask you to solve for the average atomic weight of that element because it's already on the periodic table. They'll probably ask you something like this. So for isotope 1, I'll write it over here on the side. So I'll call it I1. We have the mass, and then we have the percentage. For isotope 2, we currently don't have any information, mass or percent. Can we find either of these values before we start calculating? Yes, we can. So we know there's only 2 isotopes, and we have the percent for one, so how would we get the percent for the other one? We are going to subtract 100 minus 50.69%. So the other isotope is 49.31%. Before we do any calculations, do you notice how 50.69% and 49.31% are basically the same thing? It's almost a 50-50 ratio between these 2 isotopes. If you were, say, running at a time on your exam, didn't have time to go through these calculations, you know the mass of this isotope is 78.9, the average is 79.9, and then the ratio of them is a 50-50 ratio. Could you kind of guess what the answer is going to be?
Yeah.
What would the other isotope have to be without doing any math?
81.
So this is the middle. If we have a number here, it's basically 78.9. The middle number is 79.9. What do you have to average with 78.9 to get here? It's going to be 80.9. So do you see how if you average this and this, you get this? So I haven't done any math yet, but I'm kind of leaning towards this answer. And if you're taking your exam, I'm not telling you to do this, we have enough information to actually calculate it, but say you're running out of time and you are pretty sure that this is close to the answer and there's no answer choices close to this one, you can go ahead and, with a little bit of confidence, pick this answer. That's only if you're, like, say, running out of time. But we're actually gonna solve this problem. The average atomic weight is 79.9 AMU. And then we set that equal to the percent of the first isotope, which was 50.69, divided by 100. So I'm gonna immediately put that in as 0.5069, times the mass for that isotope. And here, make sure you put all of the decimal places. Plus, the percentage for the second isotope, we said was 49.31 over 100, so it's going to be 0.4931 times the mass of the second isotope that we want to solve for. Now from this point on, it's just algebra, so I'm not going to show any more work. I hope you guys are comfortable with doing algebra. They assume so when you start this class. And when I plug this into my calculator, I get 80.90924, and then so on, AMU. So it's exactly what we guessed it to be. They won't always be this nice, but if it's a 50-50 ratio and they gave you the mass of one and the average, you know what the mass of the other one is. And then you plug straight into this equation and solve for x. Okay, if you guys are okay with that, I'm not gonna do this problem. I'm gonna move on. Where would you find the answer to this problem? Not online. I'm asking you for the average atomic weight of gallium. So you can do this problem and check your answer by the average atomic weight in the periodic table, because these are actual numbers. I made sure to put real isotope abundances and their masses. So if you guys are okay with that, it's honestly just plugging into this part of the equation and then solving for this part. It's just more math and more calculator work. And I think there's a few more important concepts I'd rather get to than spend more time on this. If we have time at the end, I can always come back. Is the sign-in sheet still moving? Please say yes. You guys have it? Yes. Okay, great. Did it skip a row? Alright, we'll figure it out at the end. And if it really comes down to it, I'm just going to pretend like that first sign-in sheet is the same as the second one, and everyone who was here for the first hour stayed for the second hour. Do any of you plan on leaving early? I really don't mind if you do. I'm just supposed to send out 2 of them, but I can just assume everyone stayed for the whole 2 hours. That might be easier on everyone, especially me, because I have to manually go in and put every one of these names into numbers. So I hope you guys are writing neatly. Okay, I might end up doing that. This is nonsense. Okay, the next part of the class. Before we name any of these compounds, I want to point out a few differences between the compounds that you guys have learned in this class. There's 2 main categories, those being molecular versus ionic compounds. We can make a quick list of characteristics to distinguish between the 2 of these things. Anybody know anything about ionic compounds? Yes. We need a metal and a non-metal. Do we always need a metal and a non-metal? Oh, yes. Well, polyatomic ions are made up of non-metals, correct? Thanks for pointing that out, though. Because polyatomic ions are super important. How many of you have memorized all of them? All? Okay. Most of them, like the common ones. Please make sure you know those. You need a metal or a non-metal. What else do we need? We need charges. So ionic compounds are made up of ions. We've already said that ions are elements with the same number of protons but a different number of electrons. If we have a different number of electrons, what does that do to the charge of the atom? So if I donated electrons, I now have a positive charge. And then if I gained electrons, negative charge. Are metals positively or negatively charged? Metals are positive. What are those called? And the nonmetals have to be negative. Those are your anions. And then the bond that's formed is called an ionic bond. These compounds are called ionic compounds. What about molecular compounds? What are those made up of? Two or more nonmetals. Are they charged? No. So when we form them, we don't worry about the charges. It's just how many of each one we have. We'll get to it eventually. If something comes up, I'll talk about it. And then we said ionic compounds were made up of charged species. Is the compound itself charged? No. So ionic compounds are overall neutral. This is a very important concept. It's made up of charged particles. However, when we form the compounds, the positive and negative charge has to equally cancel and form an overall neutral compound. So from looking quickly at this list of elements here, or list of compounds, are these molecular or ionic? I heard, they are molecular compounds. And the way we go about naming molecular compounds is the name of the first element, if there's no subscript, it's just normal, and then the name of the second element, and it has to end in IDE. Now, if there's a subscript here, we also need to add prefixes. So if there's one, it's mono, two is di, then tri, tetra, penta, hexa, hepta, octa, all of those. If the first one is one, we don't add mono. That's the only other rule here. So if we have NF3, I want you guys to tell me what the name would be. Nitrogen, tri, and then fluoride. So the beginning and the end of the second word changed because we have a prefix and a suffix. What about B, N2O? That was correct. Dinitrogen monoxide, not dinitrogen oxide. What about N2O4? Just carry the word down there, and then it's going to be tetroxide. Oxide. I'm not very good at spelling. What about D? SF6. What about PCl5? And then S2F10. Great job. These are probably easier than how they would be on the exam, only because I've established this entire group as molecular compounds and we were following the same pattern. On your exam, you're going to hit a question and it's going to say, what is the name of this compound? And you might have answered a question previously that had an ionic compound, and you might be thinking about ionic compounds, and so you might answer it incorrectly. So please, please, please be aware when you first get to a question that you're identifying it as molecular or ionic to begin with, because they're named differently. Now, what is this group of compounds called? These are ionic compounds. How do we name ionic compounds? It follows almost the same pattern as molecular. So first, we write the name of the first element. Then we write the name of the second element. If it's an element, it's an IDE ending. If it's a polyatomic ion, however, the ending stays the same. So elements are changed to IDE, polyatomic ions keep their endings. So CaCl2, calcium chloride. Thank you for not saying calcium dichloride. But however, on your exam, you may be thinking about molecular compounds, you see that, you're like calcium dichloride. This is ionic. Calcium is a metal. What about B? Ca3PO42. Na2O. Sodium oxide. NaHCO3. So there's sodium bicarbonate is one of the names. Another name, sodium hydrogen carbonate. So HCO3 minus has two names, bicarbonate or hydrogen carbonate. You have to know both. I'm not going to write out the other one. Hydrogen carbonate, sodium hydrogen carbonate. Actually, you just have to be able to recognize both because it's multiple choice. Sodium hydrogen carbonate. AlClO3, aluminum. I love how you guys started saying the second one first. What is it? Chlorate. So there's 4 of them for these ones. The rule for all polyatomic ions is 1 more oxygen ends in ATE, 1 less oxygen ends in ITE. So these 2 are going to be our 8, and then these 2 are going to be our ite. We'll start by naming the ones in the middle. So this has to be chlorite, chlorate. Now notice there's another oxygen even after that. So we have to go to prefixes as well as the 8. So this is now perchlorate. And then this one, hypochlorite. Now I have a question for all of you. Could you tell me what that is? This is bromate. If you notice in small text, I think, on that table they ask you to memorize, it says, it has all of these listed, and it also says halogens within the same group. So bromine and iodine follow the same naming system, not fluorine though. Chlorine, bromine, and iodine can all be named using this. We would just change chloro to bromo or iodo. So if you see per iodo acetate, maybe not that one. Bromate, iodoacetate might be the answer. Okay, I would just look them up, but you have to know chlorine, bromine, and iodine. They're not going to list all of them in the periodic table because it's the same pattern of names. That was just a note about the chlorate. And then our last one, AuH2PO4. This one. So what's the first metal? Gold. So if you know your polyatomic ions and you know something's an ionic compound, these are very easy to come up with the name because you just say their names. It's a tad more difficult to go from the name to the formula because now you have to do the work in putting the charges in the right places. So forming ionic compounds. We're always going to write the metal first, then the nonmetal, and we are going to swap their charges so that it's the subscript of the other element. What I suggest is every time you have to write out the formula for an ionic compound is to write both individual charges first. So potassium nitride, ionic or molecular? How do you know it's ionic? Potassium is a metal. What is the charge of potassium? How did you guys know that? Yes, it's in that first group of the periodic table, which is called alkali metals. What's the second group called? And it has a charge of? And then the group that starts with boron, +3 charge. We don't worry about that next group with carbon. The group that starts with nitrogen, the charge? -3. Oxygen's group. And then the group that starts with fluorine, -1. What are those called? And then our last group on the periodic table, noble gases. What's the noble gases charge? 0. They do not have a charge. We're not forming ionic compounds with noble gases. So we said potassium is K+. What is nitride? N minus 3 minus. This is not NO2 minus or NO3 minus. Nitride tells us it's an element, not a polyatomic ion. The IDE ending tells us it's an element. So what we do from here is the number that's up here becomes the subscript for what's down here. So there's a 1 up here that we don't write. The 1 is going to be the subscript for nitrogen. The 3 is going to be the subscript for potassium. So potassium nitride is going to be K3N. Let's go to the second one. Strontium nitrite. What is strontium? Tell me the symbol and the charge. And then what is nitrite? NO2 minus. Now when we switch these charges, this 2 is going to be the subscript for the entirety of nitrite. And then this 1 will be the subscript for strontium. So it's going to be SR. We have to put parentheses around our polyatomic ion, NO2, 2. What about cesium nitrate? What is cesium? Symbol and charge? CS, +1 charge. And then nitrate is NO3 minus. So notice how this is a little bit more difficult because you have to know where to get these charges from and you have to know how to write down your polyatomic ions. This 1 is going to go here and this 1 is going to go here. So it's just going to be CS, NO3. In this case, we don't need parentheses because there's only 1 nitrate. The next one, barium sulfide. Barium, Ba2+, sulfide, S2 minus. IDE ending says it's an element. Then we switch these charges, we get Ba2, S2. Now what do we do? we have to simplify to the lowest numbers when we do ionic compounds. So it's just going to be BAS. And the reason we do that is because we just want to write down how many of each one we need to get to a neutral compound overall. The whole point of swapping these charges is so that the charges cancel out perfectly and we get a neutral compound. So instead of saying we need 2 bariums and 2 sulfurs to get a neutral charge, we can actually accomplish the same thing with just 1 barium and 1 sulfur, because it's a +2 charge from here and a +2 charge from here. This is saying we need a +4 charge total and a -4 charge total. But we can accomplish the same thing with just 1 of each. That's why we simplify the subscripts in ionic compounds, not in molecular compounds. If you simplify the subscripts in a molecular compound, what does that give you? The empirical formula. And we will talk about that a little bit later, but yes. So, francium sulfite. Francium, Fr plus, sulfite, SO3, 2 minus. So, francium, Fr, 2, SO3. Aluminum sulfate, Al3 plus, sulfate, 2 minus, SO4, 2 minus. So it's going to be Al2, SO4, 3. Sorry. Lead 2 phosphide. What does that 2 represent? Does that tell me I have 2 atoms of lead? It is the charge of lead. So it'll be Pb, 2 plus, and what's a phosphide? P3 minus. So this answer is Pb, 3, P2. And actually, I just remembered a mistake. We named these compounds previously. Do you guys see anything wrong with any of the ionic compound names that we wrote down? So I forgot that gold is a transition metal. If you have a transition metal, when you name the compound, you need Roman numerals. So what is the charge of gold in this compound? So we have Au, H2PO4. If you write H2PO4 by itself, what do we have? H2PO4 with a charge of -1. Therefore, because there's no subscripts here or here, gold has to have a charge of +1. So this is actually gold, Roman numeral 1, dihydrogen phosphate. I'm sorry, I did not catch that quicker. Transition metals, even though we can easily go to the name, we also have to add that Roman numeral there. Silver 1 phosphate. I'm not going to write down the ions. So silver has a +1 charge. If this wasn't given here, could you guys still come up with this formula? They don't have to give you the Roman numeral for 2 transition metals, silver and zinc. Silver always has a +1 charge, even though it's a transition metal, and zinc always has a +2 charge, even though it's a transition metal. So silver is Ag +1, phosphate is PO4 3 minus, so this is going to be Ag3 PO4. And then radium cyanide. Radium is in the second group in the periodic table, so it's Ra 2 plus. Cyanide is one of your polyatomic ions. Which one is it? Cn minus. So this is going to be Ra Cn parentheses with a 2 on the outside. Okay, we're about halfway through the SI session. Is the sign-in sheet still moving? Please say yes. Okay, great. I'm going to use one sign-in sheet. There's no way I'm going to do it again. We're not passing it around again. For this next part, you'll understand. I should have given you this. This next part is the fun part, calculating moles. So in chemistry, the SI base unit for amount of a substance is moles. This is the SI base unit in chemistry for amount of a substance. This diagram, if you guys have the little times and division symbols printed on your paper, I tried to cover them. For some reason, it didn't really translate when you guys printed them. I want you to go ahead and cross them out. That's not how you should be doing these problems, and I think one of them is wrong anyway. So like division, multiplication, symbol, the only reason I put this diagram here is because it shows that if you have moles, you can go back and forth between moles and atoms or molecules. The conversion factor that allows you to do so is Avogadro's number, 6.02 times 10 to the 23rd. This number, however, written this way is incomplete. How do we properly write out any number? It's the number as well as the units that go along with it. So what are the units for Avogadro's number? Atoms or molecules. So 6.02 times 10 to the 23rd atoms or molecules for every 1 mole. And then what is our units for molar mass? So it's going to be the amount of grams in the periodic table, also for every 1 mole of substance.